Today we are going to hopefully wrap up our study of thermodynamics, and then next class on Thursday I'm going to give you just a surface level introduction to waves in strings, the physics of sound essentially. Let me give a quick review of what we are learning. We are learning about thermodynamics, and in particular, we have the first law of thermodynamics. It says the change in internal energy is equal to Q minus W. And the work is defined as the, plus or minus the area under the graph in the PV diagram. So if we have a PV diagram and a process like this, we would get the work by just finding the area under that. Of course, we don't know how to find the area underneath such a shape, so we'll only have straight lines to find the area under. And we also know that delta U is equal to N times CV times delta T always. Okay, where CV is this weird constant that deceptively is called specific heat at constant volume, but when we're talking about delta U, it doesn't matter constant volume, constant pressure, constant temperature, or what. It's always the same. We get 3/2 R or 5/2 R, depending if it's monatomic or diatomic. And then we learned about these different processes for constant volume, the work equals 0, and the heat is then equal to delta U, so it's equal to N CV delta T. That's called isovolumetric. And for a constant pressure, also known as isobaric, then we have the work is equal to P times delta V, and the Q is equal to N times CP delta T, where CP is equal to CV plus R. And that means it's equal to 5/2 R or 7/2 R. And then we know that the network is equal to the area enclosed, plus or minus, depending which way we are closing our area. If we go clockwise, it gets a plus sign, and if we go counterclockwise, it gets a minus sign. And the efficiency is then defined as the net work over the heat input. And that's kind of where we left it last time. And today we're going to practice that with another thermodynamic cycle. And then we're going to talk about the most efficient possible engine, so that we can know if, let's say we get a 30% efficiency, we'll know if the most possible efficient engine in those conditions would be 35%, then 30% is pretty good. If the most possible efficient engine were 90%, then 30% is not good. Okay, so let's start with just a cycle. So we have points A, B, and C, and we're going to start with 1 liter of gas at 1 atmosphere, and it's going to expand up to 3 liters with a pressure of 3 atmospheres, going from point A to point B, and then it's going to stay at constant volume, and the temperature or pressure is going to decrease down to 1 atmosphere, going from B to C. And then finally, keeping it at constant pressure, we kind of crank it back to 1 liter in volume. And we're further going to suppose that the initial temperature is 300 Kelvin. So we know that there are these isothermal curves that kind of fill the space. So we can see when the temperature goes up and when it goes down. And we want to find everything. We want to find the efficiency and the work output and the heat input, all of those things for this engine. So the first thing I think we should do is convert our units into the right units. So 1 liter, there's 1,000 liters per cubic meter. So this is the same as, change my color, 0.001 cubic meter, and the 3 liters is 0.003 cubic meters. 1 atmosphere is the same as 1.013 times 10 to the 5 pascals, and 3 atmospheres is 3 times that number, so 3.039 times 10 to the 5th pascals. So we've got our units, and we probably, we need to know if it's monatomic or diatomic. Let's say it's a monatomic gas. And we are going to go ahead and find the number of moles and the temperatures at points B and C as sort of precursors. We need to have that information. So the number of moles, how do we get that? Anyone remember how to find the number of moles?
Ideal gas law.
Yeah, that's the only thing we can use. Anytime we don't know how to figure something out, it's going to be the ideal gas law. So that says PV equals nRT, so we can just rearrange that. N would be PV over RT. And that's going to be, let's pick point A. So if we pick point A for P and V and T, as long as it's the same point for all 3 PV and T, it should work just fine. So that's 1.013 times 10 to the 5th times 0.001 over 8.31 times 300. That's 0.041. Okay, and then we want to fill in our temperatures at points B and C also, because we're going to need to find a delta T at some point. So to find TB, we just write the ideal gas law at point B, and then we write it down again at some other point. I'm going to pick point A since we already know all of the values at point A, and then we divide those equations. When we do, the N and the R cancel, and the P's don't cancel because the pressures are not the same, and the V's also don't cancel because they're not the same. So nothing else can really be simplified, and we get that TB equals TA times PB VB over PA VA. So that's going to be 300 Kelvin times. I'm going to do these pressures and volumes in atmospheres and liters because the units are going to cancel anyway, and it's a little easier math that way. So the PB is 3 atmospheres, and the VB is 3 liters, and the PA is 1 atmosphere, and the VA is 1 liter. So those liters and atmospheres just cancel. Just gives me a total of 9 times 300K, which is 270 degrees Kelvin. That's my TB. And now I can do the same thing to find TC. So we just write down PCVC equals nRTC. And we could pick point A or point B. Let's pick B. PB, DB equals nRTB. It really doesn't matter what's the other point we pick. I didn't put any thought into that at all. I just picked one. And then I look at my pressures and volumes, and I notice that the volumes at point B and C are the same. So they're going to cancel out. But if you don't notice they cancel out, that's okay. You're going to put numbers in there, and then they're going to cancel out. So TC equals TB times PC over PB. So that's 2,700 Kelvin times 1 atmosphere over 3 atmospheres. So that's going to be 900 Kelvin. I'm just going to fill those in to my drawing just to give me a nice visual that will make it a little easier for me. Okay, so all of that work, finding the number of moles and finding the temperatures, is sort of just filling in background information. Now I want to find the work, the network. And that's just going to be the area. And since my shape is a triangle, that's the area enclosed. So that's just 1/2 base times height. And the base of this thing is 0.002 meters cubed. So I'm going from 1 liter to 3 liters, that's 2 liters, or 0.002 meters cubed. In other words, just subtract the 2 volumes. And the height is the difference between the top and the bottom. So it's 3.03 minus 1.01. So what we get there is 2.026 times 10 to the 5th. That's 202.6. And because I was very careful to keep things in pascals and cubic meters, I know that this is going to be joules. That's the unit we should have for work. Okay, are there any questions how I got the 0.002 or the 2.026 times 10 to the 5th? All right, so we found the work. Now we need to find the heat input. And just like we did last time, I'm going to make a little table so we can, without actually computing stuff, determine where the heat is going in and where it's going out. So we're going to make a little table. Going to have going from A to B, and then B to C, and C back to A. And we're going to find the sign of delta U, and the sign of W, and the sign of Q. And remember how this works. If we go back and look at the first law of thermodynamics and rearrange it to solve for Q, we get Q equals delta U plus W. So by looking at the sign of delta U and the sign of W, most of the time that will help us find the sign of Q without doing any work. So can anyone tell me how we know the sign of delta U? What is it that tells us if delta U is positive or negative? Do you guys remember that from last time? Delta U is internal energy of the gas. So how do we know when the total energy of the gas has gone up or has gone down? What variable out of P, V, and T is the one related to the energy of the gas?
It's if the temperature goes up or down.
Yeah, the temperature is related to the energy. So if the temperature goes up, then the total energy has to go up. Assuming everything, you know, well, not even assuming the number of particles hasn't changed. That's the only thing we're assuming there. So does the temperature go up when we go from A to B? Yeah, it does. So delta U is positive. What about from B to C? What happens to the temperature? Just show me with your thumb. Does it go up or down? Going from B to C. What happens to the temperature? Going down. So that's a minus sign. And then going from C to A, what happens with the temperature? Goes down again. Okay, so we've got the signs of delta U. Now we look at work. The sign of work is positive when the process moves to the right, and it's negative when it moves to the left. So going from A to B, we move to the right, so we get a plus sign. Going from B to C, it doesn't move to the right, so it's not positive. It doesn't move to the left, so it's not negative. The only number that's not positive or negative is 0. So no work going from B to C. We can also think of that as just a characteristic of an isovolumetric process, or we could say there's no area underneath a vertical line, or we could say if the volume doesn't change, that means nothing's moving, and if nothing's moving, there's no work done. A whole bunch of ways to sort of see that the work from B to C is 0. And then from C to A, because it moves to the left, we get a minus sign. Okay, great. So now we can find the sign of Q. When we have a plus sign for delta U and a plus sign for W, we must get a plus sign for Q. When we add those together. When we add a negative thing and a 0 together, we get a negative thing. And two negatives make a
positive.
I tricked you again. I got you guys last time, and I got you again this time. Two negatives make a negative, right? Because we're adding them together. You guys are too heavily conditioned by your math teachers. You should thank them for conditioning you. But it's two negatives, we add two negative numbers, we get another negative number, okay? So we only have to find QAB. We only have to find QAB. However, process A to B is not one of our 4 fundamental processes. So we don't have a formula. There's a specific heat if it's a constant volume process. There's one if it's a constant pressure process, but if it's like this, it's neither constant volume nor constant pressure. So there's 2 ways we can get the QAB, okay? Let me kind of split it up here. Okay, method number 1. Well, we know that delta U equals Q minus W, so Q equals delta U plus W. So if for A to B, we want to know Q, then we can just find delta U for A to B and work from A to B. Okay, so that's one way. We just find delta U and we find work and we add them up. Okay. Method 2. Second method, for a cycle, let's say a complete cycle, then delta U is always equal to 0. Why is that? Because we're starting at point A, where the temperature is 300, and we return to point A, where the temperature is 300. So the temperature, by the time we get back to our starting point, the temperature is back to its starting point, and therefore there's no delta T for the cycle. So because of that, that means that Q for the cycle minus W for the cycle has to be 0. And we already know the W for the cycle. So we could say that Q for the cycle equals W, which is my network. And that would be QAB plus QBC plus QCA. And as I said, we know the network, and we can find QBC and QCA because they are isovolumetric and isobaric. And that will let us find the QAB. So it's the same amount of work either way. We have to compute two different numbers and add them together to find the QAB. Doesn't matter to me which method. I think they're both just as good. So I don't know. Let's do the first method. The first method, for that method, we have to find delta UAB, which means N CV delta T going from point A to point B. And we know N is 0.041. And CV, because it's a monatomic gas, is 3/2 times 8.31. And the delta T, if we go back, we're going from 300 up to 2700. So that's a delta T of 2400. Okay, so pretty easy, not too hard to find delta U once we've found all of that information. And that's 1,220, I'll just round it, 1,227 joules. Okay, any questions about finding delta U for segment AB? Okay, then let's look at finding the work. To find the work from A to B, we find this area. So basically, to find that area, we find the area of the triangle and the area of the lower rectangle and add them up. We already know the area of the triangle, so it's not that hard. The work AB equals the area of the triangle plus the area of the rectangle, and we already know the area of the triangle. That's the network that we found, 202.6 joules. So we just have to find the area of that rectangle. 202.6 plus base times height. The base of my rectangle is 0.002, and the height is 1.013 times 10 to the 5th. So 0.002 is the base, and the height was just 1 atmosphere, or 1.013 times 10 to the 5th. So that is 202.6 joules also. So the work AB is just 405.2. And therefore, the QAB is 1,227 plus 405.2. That looks like 1,632 1,632.2. 1,632.2. Okay, if we had gone the other route, finding QBC and QCA, we would get essentially the same number except for possible round off error. It might round slightly differently, but it would be around 1630 joules. Okay, any questions about that on method 1? If you want to test yourself, you can work out method 2 later on and show that you get the same thing. That'll probably be good practice. Finally, to get the efficiency, that's going to be the net work over the heat input, which is 202.6. And then the heat input, according to our table, is only QAB. That's the only place where there's heat input. So that's 1632.2. 0.124, or we could call that 12.4%. Multiplying by 100 turns it into a percent. All right. Any questions? So this is a pretty generic example of what we can do. Again, like I said last time, this problem, it took us like 20 minutes. So it's a little long for a problem on a contest, but it could be split up into a couple. The problem 1 might be find the number of moles and the temperature at each point, and problem 2 might be find the network and the heat input, and problem 3 might be find the efficiency or something like that. I don't know. But again, strategically, if you find you cannot find the number of moles, but you want to do this problem and the other problems, just make up a number of moles and you'll lose, a point or two for not being able to find the number of moles. But then I will grade everything as if that's the right number. And so you can still get full credit on the other parts of the problem. Even if you just don't know how to find the temperatures of the number of moles, and that's problem number 1, and problem number 2 says find the heat input and the net work, if you make up numbers for the temperature and number of moles, and and you can show me that you know how to do that, assuming you know the temperatures and the number of moles, I would still grade that, even if you crossed out problem 1 and just picked problem number 2. So, but best if you can practice, problems like this, the problems on the supplemental problem sheet on under course content. And then, if you can do this problem completely, you've got maybe 3 or 4 problems just knocked out, on the contest. Okay, any questions about any part of this problem? No questions? Okay, so the last thing that remains is to try to understand the theoretical most efficient engine possible so that we can compare. We don't want to compare this engine with 100% efficiency because we can never get, even theoretically, we can never get 100% efficiency. But the most efficient possible engine was invented by a French scientist named Sadi Carnot. Okay, before I get into how that engine works, I want to remind you of this picture that I made last time where we have a cold place and a hot place. And we want to connect them and just let the heat flow from the hot place toward the cold place. Then when we build an engine, we are basically making a machine that takes some of this heat and converts it into work. And so the way this works is that, you know, maybe we have 100 joules of heat flowing from the hot place, 80 joules of heat goes to the cold place, and that leaves 20 joules of work output. So that would be a 20% efficient machine. Now, if we reverse this machine, so that machine, maybe that machine runs kind of like that. Okay. So if we run it backward, then what happens is this reverses the flow of heat. And what we get is heat. Here, I'm going to copy this thing. We get heat flowing from our cold place toward the hot place. And then our QH is the heat going into the hot place. So the work also changes direction. So what would this machine be? It would be a machine that takes 20 joules of work and encourages 80 joules of heat to go from the cold place to the hot place, making the hot place hotter and the cold place colder. So do you guys know what this machine is called? I bet some of you have one of these in your house. Did we get a chance to, maybe we didn't talk about this machine last time. Does anyone have one of these?
Air conditioner?
Yeah, an air conditioner or a refrigerator. Okay, that's what those things do. It's actually pretty slick to, instead of, let's say you wanted to heat your house, a heat pump is another example of this. You can spend 20 joules of energy with this machine to make a total of 100 joules of heat come into your house, using the outside as the cold place and the inside as the warm place in the winter. And so it's much more efficient than just burning 20 joules of firewood and getting 20 joules of heat. You can turn the 20 joules of energy into 100 joules of heat. So it's very efficient compared to just a furnace. But that's a heat pump. We can also use this to cool a place down. If we're using it to heat a place, we call it a heat pump. If we're using it to cool a place down, we call it an air conditioner or refrigerator. Okay, now unfortunately, when you try to build this machine and make it go backward, you know what's going to happen is heat is kind of leaking back. It's trying to leak back. Maybe we do this. So heat is kind of leaking back while you try to run this machine in the counterclockwise direction. So it's not as good as it looks. But what Carnot did is he invented a machine where heat does not leak back, okay? Heat leaks back because heat spontaneously flows from a hot place to a cold place. So what he did is he devised a machine. That's not the Carnot engine. His machine looks something like this, where we have isothermal lines on the top and bottom. So we could kind of think of those as isothermal lines. And then adiabatic lines on the sides. Those are the ones where Q equals 0. For isothermal, delta U equals 0. So the special thing about this machine is that there's no spontaneous heat flow. 2 of the sides are adiabatic, so there's no heat flow on 2 of the sides. So this sort of leakage cannot occur during the parts on the side. The isothermal parts, well, remember how isothermal works. It works by making sure your engine is in an environment that's the same temperature as it. So the heat flows into or out of the machine, but maybe it's sitting in an ice water bath, and the temperature of your gas is 0 degrees C, and the temperature of the ice water bath is 0 degrees C, and heat flows into or out of the gas to make sure it stays at 0 degrees C. So although there's heat flow on the isothermal legs, it is not heat flow from hot to cold. That heat flow from hot to cold, we cannot reverse. It is statistical in nature and we can't really stop it. But the heat flow from cold to cold, you know, one temperature to the same temperature, that is a reversible process. So what he made is a perfectly reversible machine. And then he argued the following. He said, hey, I've got a perfectly reversible machine, and nobody can make a machine that's more efficient than this one, because if they did, look what we could do. We could take their machine, supposing their machine is more efficient than my machine. Maybe my machine, let's just say it's 15, this Carnot refrigerator takes 15 joules of work and moves 85 joules of heat up to the hot place. And then suppose further that I connect my machine as a refrigerator, and I do the following. I let it take, we're going to take 5 joules out, 20 joules comes out of this more efficient machine, and we take 15 of those joules and run my refrigerator. The Carnot refrigerator, what it does is it, you know, it flows heat that way. So it's going to take 85 joules of heat and send 100 joules of heat to the hot place. And in the process, every time we run this sort of union of the two machines, I get 5 joules of work, and I get it basically for free because my hot place, my energy source, never gets any colder. And so this would be a machine that would just take heat from the cold place and turn it into work without ever having to take any heat from the hot place. So this is a violation of what's known as the second law of thermodynamics. And there's about 100 different ways to say the second law of thermodynamics. So I'll just say it in a couple of ways and then explain why this is a violation. One way to say it is it's impossible to make a machine that has as its sole effect moving heat from a cold place to a hot place with no energy input. And that's what this thing does. You could think of this as a perfect refrigerator. You just turn it on, and without ever spending a joule of energy, it just starts refrigerating, and the cold place gets colder and colder and colder, eventually reaching 0 degrees Kelvin, and with you do nothing if there were a machine more efficient than Carnot's engine. Another way of saying the second law of thermodynamics is it's impossible to make a machine that produces a work output without removing heat from the hot place, which is precisely what this does. Another way to say it is in terms of entropy, which you may have learned about in chemistry. We cannot have a machine that reduces the entropy of a closed system. And entropy is a measurement of disorder. The colder things are, the more ordered they are. The hotter things are, the more disordered. And what this machine does is the hot place never changes. The cold place just gets colder, which means it becomes more ordered. So the real sort of basis of the second law is that entropy. It has to do with just statistics. It's statistically unlikely that all of the air molecules in this room will just spontaneously, go into my closed fist through the little hole there. Just all the air molecules just go in there. But it's possible, but there's so many particles that it will never happen. And so if it did, that would be a violation of the second law of thermodynamics. So bottom line, Carnot devised a theoretical engine which would be reversible, and then showed that if there were an engine more efficient than his, that would violate the second law of thermodynamics. So what is the efficiency of his machine? Well, he was able to show that the efficiency of the Carnot engine is just 1 minus the temperature of the cold place over the temperature of the hot place. So, my hot place is the red one, my cold place is the blue one, and the efficiency, we just look at the coldest place, the coldest temperature in my engine, and the hottest temperature, and take that ratio. So for the last example, the T cold, the coldest temperature was 300 Kelvin, and the T hot, the hottest temperature was 2,700 Kelvin. And so if we had a Carnot engine, we can think of this as the max possible efficiency. That would be 1 minus 300 over 2,700. And that's 0.889 or 88.9% efficient. So for this engine that we made here, this triangular engine, its efficiency was 12.4%, but operating between that same hot and cold temperature, a Carnot engine would be 88.9%. So this one is not very good. It's not very good. It's just a, if I wanted to find out what fraction that is, it is kind of like 14% of the maximum efficiency. So 1/7 roughly of the maximum possible efficiency. Okay, so when we solve problems for engines, as a last step, we're going to want to know, how does this compare with the maximum efficiency? And to get the maximum efficiency, we just use this formula, the Carnot efficiency. And we have to just know what's the coldest temperature in my system, what's the hottest temperature, and that will tell us the efficiency of the Carnot engine. Okay, are there any questions?
Yeah, what does it say right above efficiency of Carnot, like the reversible engine? Like, what's the first word in that?
Perfectly reversible machine.
Thank you.
Sure, I'll rewrite that. Okay. So are there any other questions? All right. Well, then that is basically it for thermodynamics.